Hello everyone. Actually, we were supposed to go live on YouTube also, but for some technical reasons, we will not be able to go live to YouTube today. I will check these things from the next session. So today will be only available in Google Meet. So whoever, if any of your friends or colleagues are joining through YouTube, then please do let them know that we will not be available on YouTube for this particular session. For the other next two sessions will be available there on YouTube. Okay, so we are going to start our session today. So the topic for today's session, it was design of RCC beam, and in this session we will see what are the manual aspects that we follow while designing a beam section, and how the structural analysis and design softwares like Etabs and STAAD also does this. Okay, so let me begin here now. First of all, what we will be knowing that how the beam design concept is being developed. So suppose, let us take a beam here. So suppose this is a rectangular RCC beam, okay, and here if I draw the cross section of that beam, so this is my cross section. So these are the basic, very basics I'm beginning with. So we have some support here and here, okay, and what we have done, we have given some load on it. Fine. So due to this loading here, what will happen? The beam is going to bend in this way. So as it is a simply supported beam, so there will be no restraints at the support. It will bend in this way, right? So due to this bending, what will happen? Here you all know that at the top fibers, at the top of the beam, the top fibers will go under compression and the bottom fibers will go under tension. Okay, right. So this tension and compression, the bottom fibers which are going having tensile stress, and top fibers are having compressive stress. So the distance between these two, we can call it as the lever arm. So we are getting two opposite forces, or you can say stresses, with a lever arm. Okay, so this phenomena, this tension compression couple, so this is my tension compression couple which is divided by this lever arm at a distance, right? So this tension compression couple will be creating the resistance against the moment which is developing here due to this bending. So it will create this total mechanism, or this total phenomena will create resistance against the moment which is developing. So resistance against the moment. So this moment is the analysis moment. Okay, so this resistance against the analysis moment, this is what we call MR, or moment of resistance of a section. Moment of resistance of a section or beam, right? And then we have the analysis moment, which is my MU. Why U? Because analysis moment due to the ultimate forces, right, or ultimate load. So ultimate load means we used to consider the partial safety factors for the loads, and then we go for the design, right? So that's why this is the called MU. So these are the my analysis moment. Okay, so this moment of resistance for any beam section, we can define it in our we can find it in our code also. So if you just go to our IS 456 code in NXG, so here you can see this particular area. It has given mu equal to 0.87 Fy AST multiplied by D into 1 minus AST Fy by BD FCK. So this particular thing is defining this moment of resistance. How it is defining the moment of resistance? So if you see here, what will be the moment of resistance? How we can write it here? So the moment of resistance here, it can be this compression multiplied by lever arm, or the tension that we are getting at the bottom, tension multiplied by my lever arm. Now in case of RCC beams or any RCC sections, we are more concerned about the tension, not the compression, because we know that our RCC sections are capable enough to take the compression. Okay, so we are mostly concerned about the tension that the RCC section is taking, because due to the tension only we will be getting the cracks, right? And to resist this, or to increase its capability to take the tension, we used to provide the reinforcement bars in it. Okay, so what we need to find while designing a I can say RCC beam or RCC column or whatever RCC section it is ultimately the rebars, the amount of rebars or amount of reinforcement that we need to provide, right? So that's why if I create the form, you can say if I do the formulation of moment of resistance, so it is better to do in terms of tension. So what we can write it here, as the code has given, it is 0.87 Fy into AST multiplied by D 1 minus AST Fy by BD FCK. So this is my moment of resistance that is given in our code NXG of IS 456-2000, right? So if you see it very carefully, so this particular zone 0.87 Fy, this is the maximum tensile stress that the steel can take, and this is the area of steel. So this is nothing but the tension, means the whole tension will be taken by this particular area, and this is nothing but my length of the lever arm. So we can write it, this is the lever arm. So if we multiply this two, then we are getting the moment of resistance. Actually this mu, it will be my MR actually. Okay, so from this formula what we can find out, why this formula is given in the code, because this lever arm we can get this 0.87 Fy values, this BD FCK values we can get. So ultimately we are going to find this mu also we are getting, right? So now why they have written mu? Because we are not finding its whole moment of resistance, right? We are whatever moment, analysis moment that we are getting in the beam. So for that analysis moment, to resist that analysis moment, what is the amount of reinforcement that we need to provide, which can create this resistance against the moment? That is what we need to find, right? So that's why they have written mu. So we will be putting the value of our analysis moment here, and for this particular analysis moment, what is the resistance we need? So in terms of that, we need to find out the AST. We need to find out the AST. Okay, so if we break down this particular formula, okay, if we break down this particular formula, so we can easily find the AST equal to 0.05 FCK by Fy 1 minus root under 1 minus 4.6 mu by FCK into BD square multiplied by BT. So this is the simplified form of this particular formula given in IS 456 to find out our AST. Okay, now there is a concept, if you see here, that before getting into this formula, it is written that if the value of XU by D, so this XU is nothing but the neutral axis depth, right? We all know this XU is nothing but the neutral axis depth. So let's talk about this a bit. So suppose we have a beam like this, and our neutral axis is lying somewhere here. Okay, so this particular depth we call it as the neutral axis depth, right? So if this particular line is somewhere due to which this particular zone, which is under compression, and the other zone at the bottom of this particular neutral axis, which is under tension, are reaching their ultimate limits simultaneously. Okay, the position of this neutral axis, if it is at such position where this concrete at the top and this particular area where we have the reinforcement bars, and so it is both are reaching their ultimate stress limit simultaneously. Okay, so in this case we will call this particular section as our balance section. Okay, so how we are going to get the strain diagram? So it will be something like this, right? So it is reaching its so the stress diagram will be something like this. Sorry. Okay, so it is this particular zone is reaching its ultimate value of stress, which is 0.446 FCK, and here the steel that we have provided is also reaching its ultimate value of tension, okay, tensile stress, which is 0.87 multiplied by Fy. Okay, so then we will call it as balance section. Now what if the compression, suppose what if this particular area where with the zone which is under compression, it is reaching its ultimate value of stress, or you can say ultimate limit of stress, but the steel is not reaching its ultimate limit of stress. So what will happen exactly? So the neutral axis will go down, that means the stresses will be higher here. So we can draw the neutral axis somewhere here, right? So how will be the strain diagram? It will be something like this. The strain at the top is higher, so the compression zone is reaching its maximum value, but the tension or the reinforcement is not reaching its maximum you can say limit of stress. Okay, so what will happen in that case? What will happen in that case? So we can say that if the concrete is reaching its ultimate limit of compressive stress before the steel is reaching its tensile limit of tensile stress, then what will happen? This concrete will fail before that the reinforcement is failing, and we all know concrete is a brittle material, right? We all know that concrete is a brittle material. So that means we will have a brittle failure in the beam. So there will be no warning, there will be no you can say while before failing the beam you will not see any sign of failure, so suddenly it will fail. So in this particular condition, what will happen? what will happen when the neutral axis in this condition, balance condition, we call the neutral axis depth as our XU max. Okay, so in this condition, the XU that we are getting, this XU is greater than our XU max. So that means we have provided reinforcement in such an amount that the reinforcement is not reaching its tensile stress value, maximum limit of tensile stress, but the concrete is reaching its ultimate value of tensile compressive stress. So the concrete is failing. So that means this particular section is over reinforced. Over reinforced. Right? So if we provide over reinforced section, so what will happen? We will see this kind of phenomena and we will have brittle failure in the beam, which is not desirable. Right? So what is desirable? Can we go for this balance section? I think we cannot go for balance section also, because the concrete and the steel both are reaching their ultimate stress limit simultaneously. So here also we will have brittle failure. The concrete will fail, and the same time the reinforcement, the reinforcement will fail under tension. Right? So what is desirable? So now we can create another condition where the reinforcement that we have provided, it is reaching its ultimate limit of stress, tensile stress, before the concrete here is reaching its ultimate limit of compressive stress. So here the strain diagram will be something like this. Right? So that means the reinforcement is reaching its ultimate limit of stress, which is 0.87 Fy, but concrete is not reaching its when the reinforcement is at this particular limit, the concrete is not reaching its 0.44 FCK limit. So that means the reinforcement will fail first before the concrete fails. So now why we are allowing this, why we can allow this particular thing, or why it is recommended to consider this kind of section? Because we all know reinforcement or steel is a ductile material, right? So being a ductile material, whenever it is failing, it will not fail immediately. It will not fail suddenly. So you will obviously post-yield deformation will be there in the steel. So it will give you warning before failing. So you can have time to take you can say measure to control this fail, or measure to, you can say, resist this failure in terms of you can say structural strengthening or whatever you said retrofit and all. Right? So that's why we always try to create this kind of section where if the forces are higher, in such cases the steel will undergo maximum amount of tension before the concrete at the top is reaching its maximum amount of compression, maximum limit of compressive stress. Okay, so this kind of section, as the reinforcement is reaching its maximum tensile stress before the concrete reaching its maximum limit, so we call this as under reinforced section. So that means in this case, the XU that we are getting, the neutral axis depth, it will be always less than our XU max value. Okay, then how you can find out this AST in such cases? So obviously, as my XU is less than my XU max, okay, so in such cases, if you see here, it is written if the value of XU by D, so just to normalize it, so if you XU by D is less than the limiting value, so we got what is the limiting value. That means when the XU max is higher, at the maximum, you can say this one, when XU is equal to XU max. Okay, so till this particular point, if you want to find out the AST value, that means the steel required in tension, then we can use this particular formula, this particular process, and we can find out the AST by you can say simplifying this formula like this, right? So when your section, when you have designed a section where the XU, the neutral axis depth, is less than or equal to your XU max, okay, so we will have only one tension compression couple here. So if you see here, we have a beam. So suppose this is the XU max. Okay, so till here, what we are getting, we are having steel and concrete here. So we are having only one tension compression couple. So this reinforcement, whatever layer or whatever amount of reinforcement we have provided, it is taking tension, and the concrete above is taking compression. So we have only one tension compression couple, right, which is resisting the moment, right? So this particular kind of section are called, or this particular kind of beams are called singly reinforced beam. Singly reinforced beam. Okay, so obviously in creating this resistance, the section sizes that we are providing, it is also important, the section sizes that we are providing, because if you see the explanation given in IS 456, so it is in terms of the depth, the effective depth. Okay, and again this XU by D that we will be finding, means the XU limit that we will be finding, it is also depending on the section that you are providing. Okay, so now suppose you have some limitation that you cannot provide D, the total total depth of the beam, not more than 400 mm. And obviously we cannot increase the cannot always increase the amount value of B also, which is the width of the beam. Now if you say like how we will be deciding the width of the beam or the depth of the beam at the very initial stages. So there are some thumb rules, there are some recommendations given in our code. So while finding out, or you can say while deciding the width of the beam, we always consider that the width of the beam should not be more than the width that we are having for the walls, because if we take the width of beam more than the wall width, so in that case there will be a projection inside your room. But in some cases in small buildings you will see people are taking that, but that is different. But it is recommended for to maintain the architectural aspect that we do not take the beam width not more than you can say wall width. Now there are some recommendations in IS 13920 also, though we are not going to discuss this today. So in IS 13920 there are recommendations given that your beam width should not be less than 200 mm. Okay, so you cannot have a beam less than 200 mm width. Okay, so these recommendations also when we are designing the structure in a earthquake prone zone, seismic prone zone, so obviously we need to consider these recommendations given in the code IS 13920, but that we will discuss later. Today we are more you can say specific about the design process given in IS 456. Now how we will be deciding the initial depth of the beam? So again, the initial depth of the beam we used to consider from L by 12 to L by 10. In very higher cases we can consider a, suppose we have very higher amount of load, so in that case you may take you can say L by 10, but mostly we used to take L by 12 initially. Okay, while starting the you can say the analysis and design, so we take this L by 12. for finding the depth of the beam. Okay, so suppose we have taken depth of the beam which is 400 mm and maximum. As per architect also, you cannot increase the beam depth more than 400 mm. Okay, so in such cases, now you have higher amount of load. So you have a value of mu, which is my ultimate moment, which is greater than your moment of resistance of the section. That means this one. In this case, when your neutral axis is at the maximum limit and you are providing the reinforcement in such a way, still it is unable to resist the analysis moment. Okay, so if you see in the code, it has given the mu limit. So this is my limiting value of moment, or you can say moment of resistance, limiting value of moment of resistance. So that means for having a balanced section, this is the moment capacity that you have. Okay, so if the value of xu by d is equal to limiting value, that means xu max by d, the moment of resistance of the section is given by the following. Okay, so if your mu moment of analysis moment is greater than your moment of resistance, or you can say the mu limit value, so in such cases the singly reinforced concept is not working out. Right, the singly reinforced concept is not working. Now what is the way that we can do that? One way is increasing the section size. So section size in terms of depth, because width it is fixed, we cannot increase the width more than the wall width because it will hamper the architectural aspect, right? And again, there are, like, suppose you have provided 200 only, it has some projection which architect has allowed, but after that if you are going to increase the B, it is not going to help you. It is not going to help you, because if you see here the AST formula that we have written here, we have found out. So it is the D square. So the higher amount we are getting in terms of the depth. Okay, so now again we have some restriction to increase in increasing the depth. So we cannot increase the depth also. So what is the solution now? So we have got the section where the D value is limited to 400 mm, suppose. So the D value is restricted. B is already restricted. We all know how. Now, then how to resist this analysis moment? So here we have already provided a reinforcement due to which we are getting the XU max here. So that means it is a balanced section. So suppose we have got some mu value, suppose A, okay, and our moment of resistance, mu limit, is B. Now we know that A is greater than B here. So there are some balance moment. So A minus B is my balance moment. So I can write it mu balance. Now we do not have any other mechanism to resist this balance moment. Okay, if you cannot increase the depth of the beam. So in that case, one particular thing that we can do, that we can create another tension compression couple. There already we have tension 1 and compression 1. And we have one tension compression couple here already generated. And here, as it is a balanced section, so the concrete and the steel is already stressed at their you can say ultimate limit. Okay, so this balance moment, if you cannot provide anything else to resist this, it will fail. It will make the beam fail. So what we can do? We have to create another tension compression couple. So suppose creating the tension, it is very easy. Means tensile resistance, it is very easy. You can provide some extra. I'm not talking about layer. I'm just drawing it in such a way Even for your singly reinforced beam also, the layer can be 2 or 3. That is different. But I'm saying that we are providing, other than this tension 1, other than this resistance, we are providing another resistance which is T2. So now we have just created a tension. But to resist the balance moment, we need to have a tension compression couple. Otherwise, what will happen? If you increase the amount of tension here, tension resistance here, so what will happen? The concrete will undergo brittle failure. So we need to create a tension compression couple. So now we all know that the reinforcement, that means the steel, it is capable of taking tension and compression both. Okay, it is capable of taking tension and compression both. There is no such limitation for the steel. Okay, so this particular zone, the concrete is already stressed, so we cannot add any amount of concrete here. So what we need to do, we need to provide reinforcement here to take some extra amount of compression, which is C2. Okay, so what we have done now? Now we have created the tension compression couple, which is the additional. So this is my additional tension compression couple. So we have the first one and we have the second one. So this tension compression couple is meant to take the additional balance ultimate moment that we are having. Okay, so when we are creating such mechanism in the beam, okay, where the ultimate moment is crossing its limiting value and we are creating another tension compression couple to resist that balance moment, then this kind of beams are called as doubly reinforced beam. Doubly reinforced. But it is always recommended that we should try to keep our beam as singly reinforced as much as possible. Okay, so now wherever it is very much required, like after discussion with the architect, if it is not even possible to increase the depth of the beam or increase the section size of the beam, so in that cases we may go for the doubly reinforced section. Okay, so now for doubly reinforced section, for singly reinforced it is very easy, right? We got the analysis moment, we put the value here and we got the AST. Fine. So now here in doubly reinforced section, for the balance moment, for the balance section criteria, means for the T1 and C1, we got the AST already using the first formula. Okay, 0.5 FCK by Fy multiplied by this one, 4 point, whatever it is, I have written at the top, right? So we got this AST1. Now what we need to do, we need to find this AST2 also. So this AST1 and AST2 will give us, so this is my AST1. So this AST1 and AST2 will give me the total amount of tensile reinforcement, tension reinforcement. And here we will be having, first C1 is already taken by the, already generated by the concrete itself. Now we have given some additional reinforcement to take the C2 compression, the extra compression, right? So here also we need to find this area of reinforcement for the compression. So this is, we denote as ASC, area of reinforcement in area of steel in compression, and this whole we define it as AST, area of steel in tension, which comprises of AST1 plus AST2 in case of doubly reinforced section. Okay, so let's see how the code has given the process to find it out. So here you can see mu minus mu limit, it is giving us the balance moment that we have seen. Okay, and this balance moment will be taken by the both the tensile reinforcement at the tension zone and the compression reinforcement at the compression zone, means at the top. So here this ASC is the compression reinforcement, and this FSC is nothing but the design stress in compression reinforcement corresponding to the strain of this value. So first of all, what we need to do, we need to find the strain in compression reinforcement using this particular formula. Now what is this D dash? What is this D dash? So if you see here, from the top to the center of this, you can say rebar group. Okay, so we call it as the effective depth D. Right? Now it is for the tension reinforcement. For the compression reinforcement, from the top to the center of the rebar group. Now we have only suppose one layer of rebar, so it is center of this rebar. So we call it as D dash. Okay, so it is the effective depth for compression reinforcement. Right? So this D dash we need to find, and we can put it in this particular formula, and we can easily find out the tensile corresponding strain value, compression strain in compression reinforcement. So how will be getting this XU max? If you see table page number 70, most probably. Yeah, here in page number 70, you can see we have the XU max by D value, from where you can easily find out the XU max. The XU max equal to you can find it out from here by dividing it. The XU max by D equal to this, suppose the XU max equal to D into this one, right? So now corresponding to different grade of steel, you can find out the XU max by D value from here. And after finding the XU max from here, you can put it in the formula given for finding the strain in compression reinforcement. Now once you found the strain in compression reinforcement from here, yeah, from here, now corresponding to this strain value, you have to find out the FSC, which is my design stress. Okay, so now this strain value, this design stress value, again you have to go to page number 70. I'm showing you the process how you can do that actually. So for that you have to go to page number 70, and here you have this plot. You can see you have got the strain. Okay, and for the steel, where it is 2 into 10 power 5, right? And here we have got the stress values. Okay, so now using this particular plot, you can find out the FSC value, which is the design stress. Now it is very difficult. You can easily see that it is very difficult to find out the value of FSC corresponding to the strain that we have calculated from this particular plot, because it is very you don't know where to put your value, right? Suppose you have got 0.002, so it is okay for this. Now suppose it is 0.0029, so where to put it here, where to put it here, it is very hard. So if you refer some RCC design books available online or available in the bookstores, you will see that those RCC design books have already solved this particular problem, and they have given some table for the strain and design stress values. Okay, so the strain limit, the strain and the corresponding stress values are given. So you can refer those books for your daily design works. Okay, otherwise you have to do this hard work from here itself. So it will be obviously not precise if you are finding out from here. Right, so now once you get the FSC, so what will happen? So basically what you are doing here, so this FSC, as we know, where is this? Okay, so we had the mu balance, and this need to be resisted by the compression reinforcement at the top and the tension reinforcement at the bottom. Okay, so now as per the code, it says FSC multiplied by ASC multiplied by D minus D dash. Now what you understood from this particular formula given in the code, if you see here precisely, this FSC multiplied by ASC, this is nothing but my compression, and D minus D dash is nothing but my lever arm. So this compression multiplied by lever arm will be giving you the resistance against this mu balance moment. So once you get the FSC, and you can also put the value, suppose this mu balance is A minus B. You have some value for this, you got the FSC value also, some A, you have to find out the ASC, and you also get the D minus D dash value, because these are the numerical values only, nothing else. So you can find out the ASC from here easily. You can find out ASC from here, so A minus B, A into D minus D dash. So you can easily find out the ASC. Now once you get the ASC, so what is our concept? That T1, T2, C1 is taken by concrete and C2 is taken by some steel. Okay, so that means here T1 multiplied by lever arm equal to C1 multiplied by lever arm. Then only we can get the tension compression couple. And again here T2 multiplied by lever arm is equal to T1 multiplied by lever arm, sorry, what I am writing, C2 multiplied by lever arm. Okay, to create the second I can say tension compression couple. So now here what we have found out, we have found out the C2. We have found out the C2. Then how we can find out the T2? So here this value, we know that C2 equal to T2, we can easily write this here, right? We can easily write this here, C2 equal to T2. Now from this particular process we can easily find out. Now what is this C2? We know that C2 is FSC multiplied by ASC, and what is T2? So 0.87 Fy into AST. FSC we have calculated previously, ASC we have find out here. So ASC, you can put these values, so you got some numerical value here. 0.87 Fy is the grade of steel for you, suppose 500 Newton per meter square, and you have to find out the AST. So this AST is nothing but your AST2. Okay, this AST is nothing but your AST2, which will be creating this T2, I can say here. So what is the total amount of steel that we will be providing at the tension zone? So the total amount of steel we will be providing is the steel that we have found out for the balance section, where it is, which is AST1. I think I have written somewhere here. Yeah, AST1 for having a balance section, and then plus to create the additional moment of resistance, or you can say to create the additional tension compression couple, we are providing this AST2. So here at the bottom, or precisely I will write it at the tension zone, we will be providing AST1 plus AST2, and at the top, or precisely I will write it the compression. Already concrete is providing compression 1 C1, and for to create the additional, so we are providing ASC, which we have calculated here. Okay, now this is, I have explained when suppose here sagging and here we have hogging. So for the mid span it is applicable. What about the end span? So in end span, if you have, sorry, I think it is also sagging only, right? Yeah. So in the mid span, now here we are having hogging, right? Here it is sagging. So now the tension is at the top. So the process will be exactly same, but now the thing will be something like this. So here we will provide T1, T2, and here C1 is taken by concrete, and then we will be providing C2 to create the additional moment of resistance. So the same process, just the area where we will be providing this reinforcement will be opposite. Okay. So I hope the beam design process, means the flexural design of beam is clear to all of you. Okay. So now if I jump into Etabs software, you will see that the software is performing the same process here. So here the beam sizes I have taken, it is 200 by 350. Why 200 by 350? This column to column distance is 4000, means 4 meter. So considering L by 12, I have considered, yes, suppose it is coming 333, so I have considered it as 350. Okay, now I have assigned dead loads and live loads here, and I have created the load combination, which is dead load 1.5 dead load plus 1.5 live load. Okay, now I'll be going to design this. So if I go to design and concrete frame design and view revise preferences, so you can see this is IS 456-2000, and all these things are applicable for the column design, so you do not have to make any change here. Okay, now I will make it okay. One thing that I need to tell you, that if you select these beams, which is very important actually, and go to design, concrete frame design and view revise overrides, here you need to check what is the framing type when you are designing the beam or column. Okay, so if I click on here, there are three options: ductile, ordinary and non-sway. So if you click on ductile, it will consider IS 456 as well as IS 13920 criteria to design your sections. If you click on ordinary, it will consider IS 456, but it will consider your frame as a sway frame. And if you consider non-sway, it will design your beam as sections as per IS 456, considering the frame as non-sway frame, as obvious. Okay, so in terms of beam design or column design, these things you have to keep it in mind, like how you are going to consider the frame. Okay, so for now, suppose I'm considering, just as I'm only talking about the beam design as per IS 456, so I'm just taking it non-sway and I'm clicking on OK. So I have overwritten the section type here, and now I will run the design here. So the beam design is complete. If I just right click on here, and suppose this is the maximum value where we are getting at location 2. Okay, so it is 4 meter, at location 2 meter we are getting maximum value. So in terms of bending bottom steel, so that means obviously the sagging at the mid span. So I'll click on details here, and first, as we have I can say explain the flexural design, so I'll go to flexural details here. So if you see, let me make it a bit bigger. If you see here, that these are the definitions that we have provided: section of beam, what is the load combination for which it is critical, at what location we are seeing the design, and what is the total length of the beam. Okay, then we have the section sizes. Okay, then we have the effective cover that we have provided. Okay, So the effective depth will be 350 minus 41. Then we will be getting the effective cover, which is effective depth, which is 309. Okay. Then you can see these values are the compressive strength of concrete 25 MPa, right? So M25 grade we have considered, and grade of steel we have considered Fe4 500 for flexural design and Fe415 for shear design. Okay. Then these are the safety factors for materials as mentioned in code. Now here it is the design. So first of all, I will go to flexural design. Yeah, it is here only. Here you can see there are two different moments. One is design moment, which is given as 20.8998, and here we have the factored moment. So what is the difference between this design moment and factored moment? Why these values are different? As we know, the design moments and factor moments should be the same, right? Because 1.5 factor, after providing this factor, whatever moment we are getting, this is our factored moment. Then why these values are differing from each other? The reason is, here the Etabs has performed the design considering the torsion effect in it. If you see, there are some torsion value that we are getting. Ultimate torsion TU is 0.3697 kN/m. Now we have provision for that also in our code. Okay, so if you go to page number 85, you will see that we need to create, or we need to consider some equivalent moment due to the torsion. So if I go to 85, yes, here 85, or no, sorry, I think, let me check. Yeah, here 75. So you can see reinforcement in member subjected to torsion. So here you can see that the longitudinal reinforcement shall be designed to resist an equivalent bending moment ME1 or MEI, they have written ME1, given by ME1 equal to MU, which is my ultimate moment, plus MT, which is the moment due to torsion. Okay, and how you can find out the moment due to torsion? The moment due to torsion you can find out MT equal to TU by 1 plus capital D by B. This is the overall depth of the beam by 1.7. So this will give you the equivalent moment. So if you see here what Etabs has done, so let us solve it. So it is 0.3697. So let us see here what we are getting. So we got TU equal to 0.3697. So what will be the MT value? It will be TU 1 plus what was the formula? Let's check. D by B divided by 1.7. So it will be D by B by 1.7. So how much it is? 0.3697 multiplied by 1 plus D is 350. So I will write it in 0.35 divided by 0.2 divided by 1.7. So what is the formula answer we are getting? You all can do and let me know. Please let me know what is the answer for this. Am I getting any answer? Are you guys doing? Please do it. Let me show you. 0.7502. Point 961. Let's do it again. I think D is 350, so 0.35. Let me do it also. 0.35 divided by 0.2 divided by 1.7. I am getting 0.75. Is it correct or not? What I have written? Let me check. TU 1 plus. Okay. Sorry. It will be here 1 plus. I think yes. So it will be 1 plus here, right? So it is 0.598 kilonewton meter, right? So let's see. Yes, so you can see here the software is also giving us the moment due to torsion as 0.598. Now what we know that the design moment will be the moment, analysis moment plus the moment due to torsion. So if you do the addition of this and this, mu3 and mt, then you will be getting this 20.8998, right? So for this particular moment we will be designing our section, right? So now you can find out the AST for this design moment. Can you find out the AST for design moment? Let me once, just give me 1 second. Yeah. So okay, so can we find the AST for this design moment? So AST equal to 0.5, FCK is 25 by 500 multiplied by 1 minus root under 1 minus 4.6 multiplied by 20.8998 multiplied by 10 power 6. Why I have done 10 power 6? Because this is in kilonewton meter and I am putting all the values in Newton mm square, right? So you have to convert it into Newton mm, divided by 25, which is FCK, multiplied by B is 200, D is 309 square, right, multiplied by B into D. So 200 into 309. Find it out. Tell me whether the answer is matching with this required reinforcement given here. $164.30 are getting, so you can see it has given 164. So that means we can say that the result that we are getting from the software, it is correct here, right? Now what is this 105 minimum, regular minimum rebar? What is this 105? Why it has written here? So do you know what is the you can say minimum amount of reinforcement that we need to provide in beam? Minimum amount of reinforcement that we need to provide in beam? 0.12 BD? I don't think so. Yes, so it will be area of steel 0.85 Fy multiplied by B into D. So just find out what is the result we are getting. 0.85 by 500 multiplied by 200 into 309. Tell me what is the answer? I think I should write it in a different way. It is so 0.85 Fy, sorry, 0.85 by 500 multiplied by 200 to 309. We are getting how much? 105.06. So you can see 105. So this is the minimum reinforcement required. So even if suppose the moment is so less that the amount of reinforcement you are getting, suppose 95 mm square, just for say 95 mm square, but you cannot provide 95 mm square. You have to provide the minimum reinforcement, which is 105 mm square. Okay, so clear how the software is designing here for the flexure. Now let us understand the shear design. So shear design, do I have to explain it properly? I mean the theoretical concept, because it is very easy, we all know. What is the basic concept of shear design? So let me go to my Outlook, OneNote. So here, what is the basic concept behind shear design? So the shear VU that we are taking, it should be taken by concrete plus it should be taken by steel. Okay, so if you see here how we provide the steel, suppose this is my beam and we provide the shear reinforcement in terms of stirrup, right? So we provide stirrup like this. Okay, so if you see here, right, and these are my suppose main reinforcements. Now we have how many legs here for the stirrup? 1 leg, 2 leg, 3 leg, and the 4th leg. Now can anyone tell me which legs will be providing resistance against the shear due to the vertical load, suppose PU? So as due to the vertical load we will be getting the shear force like this. So this 1 and 2 is going to provide resistance against the shear. Then what is the work of this 3 and 4 leg, 4th leg? Why we are providing this 3rd and 4th? Is it only because we can create a general system of a ring type system just to keep it as the position? Is it because of this only? So you are saying for the reinforcement only. So this is the only purpose, reinforcement holding. Is there any other purpose of providing this? Lateral resistance of what? Beams we hardly get lateral deflection, right? This kind of deflection. So this 3rd and 4th, okay, obviously the reinforcement holding and all, it is okay. But what is the main aspect? There's these 2 legs, 3 and 4, are actually providing confinement to the concrete. Okay, so in general design it may not be that much useful, but when we are going for seismic resistant design, the confinement in the concrete is very much important. So that's why you will see that in the reinforcement design, in the design of earthquake resistant elements, so in such cases if you design a beam, it is recommended that at the support you need to provide closely spaced stirrups. Then shear will be higher obviously. So to resist the shear we have these 2 legs, and as the shear is higher, obviously there is, you can say there will be scope that this concrete is falling apart. So to keep the concrete together, that is what confinement is, keeping the concrete together. So these 2 legs are working for that purpose, keeping the concrete together, which is confinement. So the more you provide, it will provide higher amount of confinement there, along with higher amount of shear resistance, right? So that we will discuss later. Now if we are talking about shear design, so here we expect that the shear force that we are getting here, VU, it will be taken by the concrete, and also it will be taken by the stirrups that we are providing here. So that means these two legs. Okay, so what is the amount of shear taken by concrete? Amount of shear taken by concrete, it is tau c multiplied by b into d, design shear stress multiplied by my section. We will get the shear capacity of concrete. And what is the shear taking capacity of steel? Can anyone tell me? It is 0.87 Fy. Actually, it is Vs by Sv, something like this. Formula I forgot. It is something like this actually. Multiplied by D by ASV by SV. Something like this. So I think it is given in terms of ASV by SV equal to something like this. VU. So this is the shear which is taken by the steel. Okay. So in shear design criteria, first we check the tau V value. What is the design? What is the shear stress that we are getting due to the shear force here? So it is nothing but the VU by BD. Stress means force by area, so VU by BD. Then we have the tau C max, which is the maximum shear stress taken by this section. So if my shear stress due to the analysis moment is greater than my shear stress which can be taken by the section here, maximum shear stress. So in that case, we cannot go for this particular section. We have to increase the section dimension. So if tau V is greater than tau C max, then we will say that we cannot go for it. We have to redesign. That means we need to change the dimension. Right? So where we will find this tau C max? We will find it in table 20 of IS 456. Okay? So suppose now my tau V is less than my tau C max. So then it is okay, then we can proceed for the further process. Now what is the further process? Now the further process is to find out the tau C, and the tau C we can find out from table number 19 of IS 456, and it is in terms of the percentage of AST. So AST by BD multiplied by 100. Percentage of AST, we can get the tau C. After finding out the tau C, we can find out the VC. Now we know that VU equal to VC plus VS. We found out the VC. Then how to find out the VS? VS equal to VU minus VC. Right? So shears taken by the steel. So you got the shear taken by the steel. Now how you will be finding out the reinforcement amount? So we all know this will give you a numerical value, right? So we all know that Vs equal to that I have written here 0.87 Fy ASV into D by SV. Now you put this value here, you do the equilibrium. So from here you can use two particular things. One is either you put the ASV value here, sorry, not ASV, okay, ASV value here. So suppose we have two-legged T8. Okay, so 8 mm dia bar, area of reinforcement is 50 mm square. Two-legged means 2 into 50. Sorry, so it is 100 mm square. Right? So now what you can do, you can put the 100 here. You can find out the spacing required, or you can put some spacing here, suppose 150 mm spacing. So if you want to provide 150 mm spacing, what is the area of reinforcement required? Suppose my area of reinforcement required is 450 mm per meter, 450 mm square per meter. Now you decided to provide two-legged 8 mm dia bar. So the area of reinforcement is 100. So you can divide it, 450 divided by 100, how much you will get? 4.5, which is equal to 5. That means 5 number of reinforcements you need to provide in 1 meter. What will be the spacing? The spacing will be 1 meter divided by 5, so it is 200 mm. Again, for the spacing, there are some criteria given in IS 456. So if you go to IS 456, I think page number 72. No, here you can see these formulas. VUS equal to 0.87 FY ASV D into SV. Okay. So now let me see where it is. I think it is given. Let me check. There are some criteria, that's 0.75 D or 300 mm, or there is another criteria, ASB by SB equal to something criteria is given. Let me check. I think it will be here only. It is flexural design. Yeah, here you can see. What is the minimum criteria? One is 0.75 D. Another one is it cannot be less than 300 mm. It should not exceed 300 mm spacing. Or this one, whichever is less, you need to provide. Okay, so ASV value you got, you want SV. So you can multiply the cross multiplication. You can do the cross multiplication and you can find out the SV. So among these three, whichever is less, that you need to provide in the detailing. Now doesn't matter whatever value you are getting here. If the value is less than your, if your analysis value is less than all these three, then you will be providing the analysis, the spacing required as per the analysis. But it is more than that, then you need to provide as per this limiting criteria. Okay. So if I just jump into Etabs, if I show you the shear design. So as the previous one, all these informations are given about the dimensions, about the grade of steel and concrete. Now here comes the, you can see the design forces VU, 2 and TU. So here also there is some concept of equivalent shear due to the torsion. So we got a design shear force of 2.4387 kilonewton and we have torsion of 0.3697 kilonewton meter. So here if you see the design shear, we are getting 5.3963. This is the shear taken by concrete, this is the shear taken by steel. But here the shear that for which you need to design, it is much higher than the value that we are getting here. Why? Why we are getting like this? So this is nothing but the equivalent shear. So if I go to again page number 75, yeah, here. Now here you can see we have another formula to find out the equivalent shear also. This equivalent shear equal to VU plus 1.6 TU is the torsion divided by B. So let us see in details what we have got. So where is our VU? So this is our VU. So it is VU plus 1.6 TU by B. So please calculate this. 2.4387 plus 1.6 TU is nothing but 0.3697 divided by, all are in kilonewton, so you can put it 0.2. Let me know whether you are getting this value here. How much you are getting? Exactly same. So it is the 5.3963 kilonewton, even as per our manual calculation. Now for this VE, we need to design the shear. So among this VE, some amount of shear will be taken by the concrete, which is tau C into B into D. Okay, so what is the tau C value? So the percentage of reinforcement provided, if you see here, if I go to my flexural design, what is the percentage of reinforcement provided? Is it given here or not? I think percentage is not given. You can directly find out from here what is the percentage of reinforcement provided. 164 mm square. What is the percentage of reinforcement? I think here we are checking the shear for the end zones. It will not match. So for this, we need to go to, we need to close this and we need to go to any end. Suppose the maximum shear where we are getting 221. So it is showing, I think here. Okay, 348. Yeah, 348. So if I see here maximum shear. So if you see the flexural design here, at the top it is 125 mm square. So how we can find out the, so AST by BD, how much we are getting? 125 divided by 200 multiplied by it will be 309. Or you can, okay, tell me what is the percentage of reinforcement you are getting multiplied by 100. 0.2%. Okay, so for 0.2%, if I go to shear design here, now I am taking the highest shear zone, which is the end zone, okay, not the previous one. So here you can see what is the shear amount, 59 kilonewton. Okay, so we need to find out the tau C. So here you can see tau C is written as 0.33. Okay, so how we got this? If I go to IS 456 and table number 19, table number 19 here, you can see the percentage of reinforcement 0.2. So 0.2 is in between 0.15 and 0.25, and for M25 grade of concrete, in between these two. So by doing the linear interpolation, you will find that the tau C value you are getting is 0.33. Right? Linear interpolation you can do. For 0.15 it is 0.29. For 0.2 we do not know. For 0.25 it is this. So we need to find out this value. Linear interpolation you can do. Now you will see that in Etabs there is one more thing that we can see, which is that this one, this delta. What is this 1.01 delta? So this 1.01 delta is actually this one. Everything is there in the code. If you read the code properly, you will find everything here. So you can see this one. So what it says that shear strength of member under axial compression. That means you can develop, or you can say increase your shear strength of the member if your member is taking compression. So it is basically useful for the columns, but in the beam also, if you have some amount of compression, that will help you to enhance your shear. So if you see here, delta is equal to 1 plus 3 into PU. PU is nothing but the axial force that you are getting, divided by gross area multiplied by FCK. Now this delta should be multiplied by the tau c that you are getting. Then you will be getting the tau c d, which is written here in Etabs. Here you can see we have got tau c 0.33, we have got delta is equal to 1.01. Multiplying this 2, we got this tau c d 0.33 because this is 1.01. Fine. Now this is the tau c max that we have seen, that the tau v should not be greater than tau c max. The tau v we are getting 0.96. Tau c max is 3.1. From where we got this 3.1? You go to code, you will see that here in table number 20, it is written here clearly. For M25 grade of concrete, the tau c max value is 3.1 Newton per mm square. Okay. Can you see all the, can you relate the code provisions given and the software results? So as my tau c max is not greater than by tau v, so we went for further designing and we found out the AST from here. So we found out the equivalent shear, and from this equivalent shear we found out the VC. This is the shear taken by concrete, and if you minus it, 59.2805 minus 20.3841, how much you are getting? How much you are getting? Can you tell me? So 38.8964, this is the shear taken by steel, for which you need to find out the shear reinforcement. Okay, so how the shear reinforcement is being found out here? So the shear reinforcement is given in terms of ASV by SV. Okay, the shear reinforcement is given in terms of ASV by SV. So mm square per meter. How it is given? So we know that 38.8964 equal to 0.87 multiplied by 500 multiplied by 0.87 FY into ASV na. So suppose we are using, okay, let me write it here, ASV multiplied by 309, my D, divided by SV. So what is the value of ASV by SV you are getting? Tell me. 38.8964 divided by 0.87 multiplied by 500. I think we need to multiply this with 10 power 6. Oh sorry, 10 power 3, because it is kilonewton na? So 10 power 3. So 0.87 into 500 multiplied by 309. That's it, I guess. Tell me whether the result is matching with this. Point 2893 you are getting. So I think we have done some mistake somewhere. Let me check. Let me check where we have done the mistake. It is in kilonewton. Okay, so what was the formula we have written for? No, actually we want to find out this ASV by SV, right? So that's why I'm saying that I think I have done some mistake here. 0.87 Fy into ASV into D by SV, right? This is what the formula was. And we kept it here 38.8964 multiplied by 10 cube. Yeah, it is correct only. Okay. One thing. Please check it once again. Okay, it is 415. Yes. It is 415 for stirrup, right? Yes, exactly. 415. Are we getting the answer now? $348.65, but still it is not matching with this value. 371.18. Can you check it once again? $348, but we are getting some higher values then. If your calculated result is this, but still we are getting some higher value here. So maybe you can say this is the flaw of the software, but I don't think it should get something like this. So maybe we have done some mistake somewhere in some calculation, I don't know. But okay, so what we can say that it is close to our value, but a bit higher, but still okay. If it is higher, if it is low, less than the value that we are calculating, then it will be an issue for us, right? So I don't know whether it is. I need to check it later whether it is correct or we have done some mistake somewhere. So what I'm saying, all the results that the software is giving us, it is as per the codal provisions only. So some people will say like you will heard that it is I have designed it as per software, so it is the different. Your manual design will be different. No, the design concept is exactly the same in as it is given in the manual process as per the code and as it is in the different softwares. Okay, now it is up to you which particular input you are giving, which particular input you are considering to design, and which one is you are ignoring. In the software, if you are ignoring something, then the result will be coming as per your consideration. So some people used to say that the manual design results will not match your you can say software results. So this is the proof that software results are matching in case you are considering the proper input. Okay, so software is always a garbage in, garbage out. If you give garbage, it will give you output as garbage only. Okay, now why there is difference in the analysis results? Because when we are considering, suppose we are considering a frame and we are designing a beam. So what we do, we used to consider WL²/12 at the end and WL²/24 at the midspan. But it is not the case. Whenever we draw a beam like this, a frame like this, okay, it is not a fixed beam. These joints are rigid joints, so that's why the analysis results may vary, because here then you need to consider the matrix method to solve it out to get the actual value of moments, okay, in terms after finding out the displacement, and then you can do the design process as per the code. So design will be exactly the same. Analysis is changing because of the methods or assumptions that we are doing. So analysis also it will match if you do the matrix method and if you solve it as per your you can say design criteria. Okay, so this is how you can proof check your different softwares by seeing whatever output they are giving. Okay, the same thing you can do with the StatPro also. I'm not going very in depth for the StatPro because I specifically do not use StatPro for the RCC design. Okay, StatPro is one of the best softwares for steel design. Obviously, there are many people who are using StatPro for RCC design, but this is my preference that I am not using it. So if you are using StatPro, then you can see in the design result that StatPro is also giving us a similar kind of results. So what StatPro does, StatPro designs for 13 different locations. The same thing Etabs also, right? Etabs also is doing the same thing. If you see, if I open Etabs, right click, you can see it is also doing for different locations in the beam, starting from the 0 location. See 0.15. Why 0.15? Because our column thickness was 300 mm. So we need to design the beam from the face of the column. So it has left 150 mm which is embedded inside, and from 1.15 distance it is starting designing and up to the 3.85. Okay, leaving the other 150 mm the other side. Okay, but in StatPro, unless or until you are providing any offset for the column, it will consider the you can say moment from the center of the column itself. Okay, so you can provide offset to consider it, otherwise you can go for this conservative approach. So in STAAD, if you see, same locations from 0 to 4000 means 4 meter, and at every location it is giving us the mz value, that means our analysis moment. It is giving us the torsion, so you can see the torsion is 0 here. So as the torsion is 0, so that's why in that case the equivalent moment that we are getting, it will be exactly equal to the analysis moment, that means the ME. Similarly for the, let me zoom it a bit. Similarly for the shear also, as the torsion is 0, the shear, analysis shear will be exactly same as the equivalent shear. Okay, and based on this it is giving us the reinforcement at the all other locations. You can see at the end span the top reinforcement is higher, so it is considering this thing you can do by yourself. This is detailing. Whether you want to provide 10 mm dia bar or not, that is your concept. So we do not provide 10 mm dia bar, we start with 12 mm, right? So but you are getting the area of reinforcement from here. Okay, and the bottom, obviously at the mid span the bottom reinforcement will be higher. Now why they have given 157.08 at every the total span? Because you cannot provide you can say a bar only at the mid span, right? We need to provide throughout at least 2 bars. So that's why throughout we are having 210D they have provided actually. So this is the required 131.77, and this is what they have provided. Fine, here it is the requirement, but this is what they have provided. So the minimum they have provided throughout. For the shear design, you can see the same thing. Vy, there is no moment, no torsion, so the same thing will be the equivalent shear. Okay, and as if you calculate as we have done, actually it is not given very in detail in STAAD. So if you do the calculation as per this Vu and Mx value, you will find that this is the number of reinforcement required. Okay, so in STAAD the results are not that much in depth. Okay, so you have to calculate by yourself and you need to check whether this is the correct criteria or not, or correct result or not. Okay, so I hope this design of beam, the manual process and how the software is performing the design, it is clear to all of you. So anyone have any doubt, please explain the shear also. 1 and 2. Yeah, I have explained the shear, right, Rizvi? Sorry, I think I have not seen the chats while you can say taking the classes, because I'm using only one screen. So now if you have any doubt regarding this or any question regarding this, you can always ask me. Yeah, actually we do have a course on RCC superstructure design till now, for now, which is an ongoing course. We have already uploaded almost 40 sessions there. So 40 sessions, you can say it's about 60 to 70 hours already we have covered. So it is all about from the bottom to top about a building, and it is not covering the foundation system because it will be of a different course. So if you want to join, you can always check it in our Android app, or if you are using iOS, our app. Okay. So as I was saying that if you see STAAD moment results, moment diagram, it is giving from the center of the column. Okay. And if you see for Etabs, it is giving the result from the face of the column. Okay, by default. Obviously, you can change these settings, but by default, it is giving from the face of the column. And if you change the column size, automatically it will change this distance also as per the column dimension. Okay, so this can be one reason. The second reason can be, now if you are designing only for you can say dead load and live load. Okay, so please do for one particular beam and check. In Etabs, again, as I have said, you have to check these design preferences. You have to check the design overrides. Okay, whether you are designing it as ductile, whether you are designing it as non-sway or sway. And in STAAD Pro also, you are giving this design inputs. You need to keep those in mind. So the result difference will be there obviously. In Etabs, we are modeling the slabs. We are considering the stiffness of the slab. If you are designing with the earthquake forces, so this slab stiffness will obviously, for rigid diaphragm it is not that much matter, it will not differ much, but for flexible diaphragms in STAAD, if you are not modeling the slab, the plate, so it will not consider as flexible diaphragm. So in that case, to consider the rigid diaphragm, we have to provide the rigid diaphragm command. Otherwise what will happen, the forces will get transferred through the beams to the columns directly. So obviously there will be higher concentration of forces on the beams. Okay, and it will lead to give us higher amount of reinforcement. So you just have to check these things. As I said, whatever you assume, whatever you give as the input, the software will give you the output accordingly. Okay, so this is the reasons actually, two different softwares having two different way of working. So once you understand how it works, then the results will not that much differ. How to model irregular building in Etabs. So there are various videos in my YouTube channel, in other YouTube channels also. If you see, modeling is not an issue, right? In any software, you can create the DXF file, you can import it into Etabs or STAAD Pro or whatever software it is. Okay, modeling is just there are different ways. You just have to see some basic videos or basic sessions of, maybe CSI also have some sessions on it. You can check that. So I hope this session that we are conducting for the next 2 days, it will be helpful for you, especially the session on 24th, which is on Modal analysis, and we expect all of you will join, and we will have more participants on it. So, and tomorrow we'll be having the column design session. Similarly, we'll be explaining how these softwares are explaining. Tomorrow, the same time, we'll be having the session on column design, RCC column design, manual design process, Etabs, and the STAAD Pro explanation. Okay, thank you and see you tomorrow.